Okay, so we'll start on page 9. First, our quick look at the calendar. Today we cover a topic called inverse functions. What do we cover tomorrow? More on inverse functions. So the fact that we have 2 days on one topic says this is an important topic. I'll also say that this is a monumental day in terms of our class because for the first time, what can you see on our calendar that's projected? Final exam. So we're getting there, more than halfway there, and this is the first time we can actually see the rest of the semester. Just barely. In the back of the room, they can't see it, but it's there. Okay, so we begin on page 9. Yes, Michael. Next Monday. Monday is like the day after Easter. Is that why you're asking? Oh, the following Monday? What's happening on, I don't know. What is it? Patriots Day. There's a Monday Friday schedule swap happening. I think it's that Friday, like on the maybe the 13th or something. So not this coming Friday, but the following Friday is a go to your Monday day classes. It doesn't affect us because we meet Monday, Friday. But yeah, good question. Okay, so in the middle of page 9, right here we begin with number 1. We'll go with Sarah. Okay, go ahead and find those two things and check with your neighbors. So what is f of 5? 13. What is g of 13? 5. So there's some kind of swapping thing happening with these two functions. 5 goes to 13. 13 ends up going back to 5 when you plug into the other function. We're going to do part B right now. It says find g of f of x. This one's tougher. G of f of x. Which one goes first? Well, yeah, what do you do first? You do f of x first. So that means g is just hanging out, waiting its turn. And in the parentheses, we're going to put f of x. What is the rule for f of x? 3x minus 2. So that's this guy replacing f of x. And then here's the tough part. It's taking the g function and applying it to something that's not x. We're applying g to 3x minus 2. Let's take a look at what the g function does. It takes whatever's in the parentheses, puts it on top with a plus 2, then divides the whole thing by 3. That's what g does. Takes whatever's in the parentheses, sticks it on top with a plus 2, and divides by 3. Well, here's what's in the parentheses. It's 3x minus 2. What's it going to do? It's going to stick it on top with the plus 2 and divide by 3. I think that's the toughest part of the problem. Did we see what just happened there? Took g and applied it to something complicated, 3x minus 2. And then we'll simplify a little bit. What happens on top? Just 3x, because the plus 2 and the minus 2 cancel. And then divide by 3, we get x. Okay, so something very important happened here. We started in the inside of the parentheses with an x. Did you guys see what just happened there in that color? What color did I select over here? Did I? I selected blue. And what happened over there? Makes green. Is that true? Yellow and blue and green. Okay, but what happens here is that ultimately we started with an x in the parentheses, and what did we end with? x. Start with x, end with x. Whatever you start with, come right back to it. What did we start with in the part A? 5. What did we end with in part A? 5. So this is something very special for these two functions. We're going to skip over part C. Do you have a guess what the answer is going to be? It's going to be x. You should check it later on. I'll just write down here, show that you get x. Okay, so now we'll give a name to the thing that we just saw there, down here in number 2. Taylor? Okay, lots of symbols, lots of words. The important thing is we are defining two functions to be inverses if they undo each other. For example, these two functions up here, f of x is 3x minus 2, and g of x is x plus 2 over 3. They are inverses. They undo each other. Okay, a little bit of notation. We'll go to Taylor. Okay, so this is a confusing thing for a lot of folks, but instead of calling this g of x, which doesn't really indicate that it has anything to do with f, we call it f to the minus 1 of x. If you start with f of x, the symbol that we almost always use for the inverse is f to the minus 1. Start with f to the minus 1 means f inverse. Don't read it f to the minus 1, read it f inverse of x. That's what it's called. And it's a moment where things can get really confusing because how much is, say, 3 to the negative 1 power? It's 1 over 3, right? I mean, that's like you see a negative power up there, it means 1 over. That's what it means. This f to the minus 1 does not mean 1 over f of x. So it's unfortunate that we have that minus 1 meaning a couple of different things. I will tell you that this 1 over, even though that's probably the most comfortable thing you've seen for minus 1, that's not the general thing. The general thing is this idea of inverse. Taking 3 and turning it into 1/3 is an inverse of some kind. It's called the multiplicative inverse. What do you get when you multiply 3 by 1/3? You get 1. What do you get when you multiply 5 by 1/5? You get 1. You always get 1. So in some sense, the opposite of 3, undoing 3, is 1/3, if you feel like 1 is a natural place to get to. And so that minus 1 that we use up there, that's not the general thing. General thing, that minus 1 means inverse. And in fact, on your calculator, we're not going to use it right now, but if you take a look at, see right above this key that says sin, it's a very religious calculator I have here, so just watch yourself. So right above it, what do you see? You see that sin and then a negative 1. That doesn't mean 1 over sin, whatever sin is. It means the inverse of sin. It's very difficult for me to say sin. It's pronounced, anybody know how it's pronounced? Sine. Okay, so I'm going to stop saying that. But that's the sine function. And that minus 1 does not mean 1 over. It means the inverse of sine. And the same thing with these next two functions. They are inverse functions. Okay, so negative 1 generally means inverse. It does not generally mean 1 over. That 1 over is just a special thing. Okay, 3. Andy. Okay, so that's what you did this morning. Put on the socks, then put on the shoes. When you go home, what are you going to do? Okay, so we're going to take off the shoes. And then take off your socks. Just restoring the original condition of a bare foot. Right. Okay, so what's the point of this example right here? Was it enough to just do the opposite of putting on your socks and putting on your shoes? No, because then you would put on your shoes and put on your socks. Yeah. Don't we have to think about the order in which we do things? The first thing we did was put on the socks. Then the second thing we did was put on the shoes. When you're going to undo it, of course, you're going to undo it in the reverse order, right? Okay, same kind of thing happens with inverse functions. Let's try number 4. We'll go to Michael. guys write down something in English, not really symbols, just English, the inverse of that thing. Okay, in English, what's the inverse of that? Oops, thank you. So first divide by 6, and then subtract 3. You guys agree? Multiplying by 1/6 is the same as dividing by 6. Yeah. What's that, Derek? Let's see. Yeah. So I guess maybe first we should have said take x, divide by 6, and then subtract 3. So let me write down. You guys actually just figured out an inverse function. First, we need the rule for the original. If I said add 3 to x, so that's an x plus 3, and then multiply by 6, that means you're taking the whole thing and multiplying it by 6, right? Well, you guys just figured out the inverse. I'll write the notation. It's here in purple. It says take x, divide by 6, x, divide by 6, and then subtract 3. Then subtract 3. These two functions are inverses of each other. As a quick check, pick your favorite number for x. Somebody shout out a number. All right, x equals 1. What do you get when you find f of 1? Plug 1 in there. One vote for 24. Agree? To check and see to see if this is right, what should we plug into the f inverse function? We should plug the 24 in, right? If 1 goes to 24, then hopefully 24 comes back to 1. So f inverse of 24, let's see. 24 divided by 6 is 4. Subtract 3, 1. Did it work? Yeah, 1 went somewhere, went to 24, but who cares? We got back to 1 when we were done. These are inverse functions right here. Okay, let's try number 5. We'll go to Brian. Okay, so I've given you a table with function values. And now we're going to try to fill in a table for the inverse function. Let's take a look at what happened up here in this red example. Where did 1 go? Went to 24. And where did 24 go? Back to 1. So we can see what happens when you go from a function to the inverse. What happens to the x and y? They just switch places. So if the original 1 goes to 2, then in the inverse function, what happens? 2 goes to 1. Can you guys just fill in the rest of that table? Okay. So let's see if we can summarize what we just saw. Number 6, Katrina. Okay, so a couple of important things there. F and F inverse, the inputs and the outputs just swap. And we know that the domain, which is the x's, would then become the range, which is the y's. So just swapping the x's and y's means you're also swapping the domain and range. That's going to be important for us too. Let's try 7 for Tyler. Okay, so let's try a couple of these. For this first one, we're plugging -2 for x. What is the absolute value of -2? 2. You guys fill in the rest of that table and then swap them for the inverse table. Did I make a mistake? All right, so we've got a problem here, right? Because, I mean, I just copied. I wasn't thinking about stuff. I just took the y's and I made them the x's. And then I took the x's and I made them the y's. I mean, that's what you're supposed to do for an inverse function. They just swap. But you guys can see right away that there's a problem in that, for example, if we look at the inverse function, then on the one hand, 2 gets sent to -2. On the other hand, 2 gets sent to +2. So what can you say about f inverse from that table? It's not what? It's not a function. right? Remember our definition for function says if you give me a single x, there's only one answer I can give you for y. But here we've got a problem because some of you guys will say that 2 goes to -2, and some of you will say that 2 goes to +2. So it's possible you can have a perfectly legitimate function. Is this absolute value a function? Yep. But it doesn't have an inverse that's a function. And let's think about the picture here. How do you know just looking at a graph if it's a function? It's the vertical line test, right? And so no vertical line hits more than once, so hooray, that's a function. What goes wrong over here? Well, it doesn't have anything to do with vertical lines. It has to do with horizontal lines, actually. Let's think about a couple of these points here. Let's plot -2, 2, and 2, 2. So that's this point, and it's this point. No problem with vertical lines, but there is a horizontal line that hits both of these. And that's why we run into the problem circled in purple there, right? And so we're going to have this thing called the horizontal line test, which will tell us whether or not the thing, not that it's a function or not, but whether its inverse is a function or not. So let's go to 9 for Joe. Okay, what can you say about that green line up above? How many times does it hit the graph? Twice. So does the absolute value have an inverse that is a function? No. So that's the horizontal line test, okay? We had vertical line test. That tells you whether or not you're a function. Horizontal line test tells you whether or not your inverse is a function. Okay, let's try this next piece of the draw, Connor. Still part of 9, draw. Okay, so go ahead and draw something in that little graph there. Anything that's increasing the whole time. Is my thing okay? This is not increasing the whole time, right? So that's no good. You need to make it increase the whole time. How about something like that? Does it have to be a straight line to increase the whole time? No. So let's be creative. Increasing, but then kind of like that. Is that increasing the whole time? That's fine. All right, keep going, Connor, in the context. What do we think about that green function right there? It has an inverse. Yes? Because horizontal lines can't hit it twice because you didn't let it turn around. Right? If it's going up the whole time, never has a chance to come back down. So they have an inverse. Okay, we'll go to Hazen for 10. Okay, so 1-to-1 is really just a fancy way of saying it passes the horizontal line test, which also means it has an inverse function. So, so looking back at this absolute value graph, does every x correspond 1-to-1 with a single y value? And the answer is no. You can find the y value of 2, which comes from 2 different x's. So 1-to-1 just means it passes the horizontal line test. So I'll say up here, this function is not 1-to-1. 1-to-1 says yes, it passes the horizontal line test. All right, so we'll go to Eliza for 11. Yeah. All right. See if you can wrap your head around that. Take like 2 minutes to really think about whether that's sometimes, always, or never true. Come up with some examples at your table. Suppose for a second that this is true some of the time, anytime. If this number out here is x, you guys point to where negative x is because that's what we're after. Negative x is the mirror image over on the other side. Whoops, negative x. And if we're saying that f of negative x is equal to f of x, what does that mean about the 2 points that I'm going to plot? What is it? Yeah, I think we're going to run into problems here. Because if f of x, if this point right here is f of x, but I'm telling you it's equal to f of negative x, then I think what we're saying is that it's at exactly the same y value, right? The y value for one is equal to the y value for the other. And if they're equal, then is it 1-to-1? It's not, right? 1-to-1 means passes the horizontal line test. It means you never have a duplicate y value. So could this possibly be true for a 1-to-1 function? The answer is no. Couldn't ever be true. Okay. This question comes from a friend of mine I met last summer. His name is RJ McDaniel, just trying to give credit. Okay, so next page. Number 12. Sam. Okay, thank you. Let's come up here to Matt for A.
It equals ft if the population is built as a function of time. What are the inputs?
Okay, so why do we care about inverse functions? Well, I want us to be able to handle sentences like this. All right, so we've got the population as a function of time. So that means that the t is measured in what? So t is years since 1900. And that means that the output is what? It's population in people. And that's for the original function. But what happens when you go to the inverse function? What happens to the input and the output? They switch. So that means that for f inverse, the input is actually what? Is the population in people. And what's the output? Is the time in years. So to tackle one of these kinds of questions, I think you first look at original function f, write down the inputs and the outputs originally. And once you've got a handle on that, f inverse just swaps them. Inputs and outputs get reversed. Let's see if we can then answer the next question. What does the inverse function represent? All right, first I want to make it clear what that even means. Suppose that I didn't ask you about what the inverse function represents, but rather what f represents, the original one. Don't change that because this is just a temporary change. But for the original function f, I might be looking for something like this. Given the number of years it is since 1900, the output of f is the population of Greenfield in that year, right? Given the year, we end up finding the population. Now we're just going to say that in reverse. What's the given for f inverse? What's the input is a population? Given a population, what does f inverse output? The year. Given a population, the output of f inverse is the year that population occurred. Is that how you spell occurred? Is there only one R? Yeah, this is a good point. So first let's talk about that. So given a population, the output is the year, right? Now for any of this to, for f inverse to be a function, then I guess we're assuming that we never had the same population in 2 different years. Is that true here in Greenfield? Greenfield's population always rising? I don't think so. I think there are some years where the population goes up and other years where the population goes down, right? There are flows. And so I think that Matt raises a good point here, that this might not even be a function. Given a certain population, let's say I want to know, when was the population in Greenfield 30,000 people? Well, maybe the answer is 2005. Maybe another answer is 1999, right? So in that case, F inverse would not be a function. So this is a really good observation to make. Okay, let's go to this last part here. Eric?
Suppose F inverse of 1400 57, right?
Okay, so let's see if we can figure out what those numbers are. 1400 is an input, but you got to make sure you know it's the input for which function? For F inverse. And what are the inputs for F inverse? It's population. So 1400 is 1400 what? Years. Is it 1400 years? It's the population. That 1400 is the input for F inverse. It's the population. So 1400 people, and what's that 57? Is 57 years after the 1900. So said another way, 1957. Okay, so you could say this sentence in one of two ways. You could say in 1957, what happened? Population was 1400. I don't want you to say that. It's true, but I don't want you to say that. Because what did you do to the numbers, the order in which they were given in the, you reversed them, right? This is a sentence that F would say. F would say in 1957, what was the population? It was 1400. This is reversed. So we need to change the thrust of that sentence. We need to make it so that it's an inverse kind of sentence. If the population is 1400, then what happened? It was 1957. Or it is 1957. Something like that. If that sentence feels awkward, try a different one. If you want the population to be 1400, you must wait until 1957. However you write that, I really need you to say the 1400 first and the 1957 last, because that's what the inverse function does. Given the 1400, the answer is 1957. So give me a sentence that reflects that, the stress of the inverse function. All right, so here's what I want us to do. We have two other examples, just like the one we did. There are answers down below. And on the next page is something called columns and cell phones, and you're going to work through all of that. I think that we'll have enough time to do all of this, and then maybe we can start what I had planned for tomorrow. We'll see, but let's see how far we can get in those two things, all right? Okay, so we're going to go ahead and jump ahead. So the homework assignment is up above. I'm not adding any more just because we're going to start the next section. But that section was kind of shortish, and this one here is a little bit long, so I want to make sure that we don't run out of time next time. So let's go ahead and start in the middle of page 13 with number 1. And I think we're up to Iris. So let's review. Okay, so we saw that earlier today. In fact, we saw all of this earlier today, so it's this is supposed to refresh our memory from the 48 hours that have passed, but this should be very current for us. We'll come over here to Sarah, number 2. You guys remember that? If it's always increasing, then it's going to have an inverse because it doesn't have a chance to turn around and fail the horizontal line test. Taylor M. Okay, so that's just X and Y swapping. We did that with some tables. Taylor L. It's actually the same kind of swapping that we just saw above. And Andy? All right, I'll read that one. f of f inverse of x equals f inverse of f of x equals x for all x, right? Do them in two orders, and we just get back to where we started. Let's go to Andy for number 2. Okay, so let's start over here with this f of 2. How much is f of 2? F of 2 is 10, right? Can you guys hold up the answer to part B? What is f inverse of 10? Hold up the number of fingers that is the answer. F of 2 was 10, so f inverse of 10 is 2. You buy that? F inverse of 10 is 2. Because we know that a function going to its inverse, the input and the output just swap. Okay, so that was kind of easy because I said find f inverse of 10 right after I asked you to find f of 2, right? So what if we don't have the answer? F inverse of 31. Yeah, you need to get 31 as the answer, right? So you could really like solve an equation. You could solve some equation equals 31. What's the equation? Yeah. Isn't that what we're after? You need the function to equal 31 as the answer. And whatever you get, well, that must have been the original x that we started with. So go ahead and solve this for x. We get 9. So how much is f inverse of 31? It is 9. And before I go to the next page, I'm going to write one other sentence here. F of blank equals blank. Yeah, we just found f inverse of 31 is 9 because f of 9 is 31. You could check. Plug 9 in. 27 plus 4 is 31. So in some cases, you can kind of find the inverse just by solving an equation, right? You wanted f inverse of 31. It meant take the whole thing and set it equal to 31. That's really different from what we did in the first part here, where it said find f of 2. Did we make the whole thing equal to? To find f of 2, did we make the whole thing equal to? Did we? We just plugged in the 2, right? So finding f of 2 is really easy. You just plug in the 2. Finding f inverse of 31 is work. It's algebra. It's not just plugging in. It's solving an equation equals 31. All right, let's try the next page. It says find the inverse function. What's that? Maybe. I have a process down below. Maybe that's what you're thinking of. All right, what was the function? It was 3x plus 4. Okay, we're trying to find the rule for the inverse. Michael, did you have a hand up? Yeah, we're going to think about order of operations and we're going to solve an equation. In the previous problem, we made this equal 31, right? Some specific number. Well, in this problem, maybe I'll call it something general. I'll just call it equals y. And then let's go ahead and solve for x. So what do we do to both sides? We subtract 4, so we get 3x is y minus 4. And then divide by 3. But then the letters are kind of funny now because that looks very strange to me. I'm used to seeing f of x, f inverse of x. So how about we change it? Instead of an x here, maybe I want to think of this as my y. And maybe instead of a y here, I want to think of that as an x. So y is equal to x minus 4 over 3. Just to kind of make it look more natural for me. I'm really used to seeing equations solved for y. with x's on the other side. So let's just swap the letters. And then the last thing, I'm trying to come up with a good name for this. What is this thing called, this x minus 4 over 3? It's the inverse, right? Well, we have a better notation than just calling it y. We call it f inverse. So this is just like a symbolic thing. I'm not really doing any math, I'm just changing the name. F inverse of x is x minus 4 over 3. Questions on that? Okay, so finding the inverse of a function is a process, and we're going to look at the process right down below. But I don't want to make it so that it's just a process and there's not really any understanding. This is an example of a function that we could have pieced our way through without doing this whole solving equations. Suppose that we go back to the original function f. You're given some number x. What do you do to it first? You multiply by 3, right? That's the 3x, order of operations, as Michael said. So first thing you do is multiply by 3. Take x and multiply by 3. And then what do you do next? And then we add 4, right? That's what the function f does. Is you multiply your number by 3 and you add 4. If you want to undo that, it's not enough to just undo it. What else do you have to do? Is change the order, right? Just like the socks and shoes thing. The first thing we did was multiply by 3. The last thing we did was add 4. If we want to undo it, we better work our way back, up this list. So instead of adding 4, what should we do? Subtract 4. Take your number and subtract 4. And then what should you do last? The opposite of multiplying by 3 is dividing by 3. That's what we did. We took our number, we subtracted 4, and then we divided by 3. So for some functions, you can kind of piece your way through like step by step, undoing everything in the reverse order. Sometimes it's not so easy. But anyway, I just wanted to mention that this idea of inverse, sometimes you can do it this way. So let's talk about this procedure here. I'll go to 3 for Michael. Okay, Brian. Okay, so let's take a look at this example. So we're going to go through the steps on the left, and then we'll do the process for this specific example. F of x is 5x minus 3. So first it says check that the function is 1 to 1. Can you guys with your arm show me what the graph of f of x is 5x minus 3 looks like? 5x minus 3 should remind you of an mx plus b. So it is a line, uphill or downhill? Uphill, flat or steep? This is really, really steep. The slope of 5 is a very steep line. If I'm at a 45-degree line, what's the slope of that line? That slope is 1. This one is slope of 5, very steep. But the important thing is, does it have an inverse? Sure, because horizontal lines are only going to hit once. Okay, we'll go to step 2. Katrina? Okay, so let's try that. So the first thing we do here is call it y instead of f of x. Okay, now you have a choice. Right now, compared to what we did up above in black, we are at, where are we now? We're at this stage right here. We made the thing equal to y. What did we do next? What was the ultimate goal going from there to there? We did swap, but I feel like we did that at the end. What was the goal from this equation, finally getting to that equation? Solve for what letter? Solve for x. Wasn't that what we wanted to do? Solve for x. Great, there it is. We solved for x. So we're at that stage right now where it says solve for x. And you can see that's not what I said to do in step 3. I said swap the x and the y. For me, I like swapping them first. If you want to swap them at the end, no problem. Let's go ahead and change all the x's to y's and all the y's to x's. So this becomes x equals 5y minus 3. And that swapping is something that we've said. A question? No. That swapping is something that we have talked about a lot today. When you go from a function to its inverse, the x's become y's become x's. We're just swapping them just like we've been doing all day. Then we get to step 4. Tyler. Okay, go ahead and solve that equation for y. I got x plus 3 over 5. Any questions on that one? Is that okay? All right. Let's go down to number 5. Joe. Okay, so this is just substituting just to make it look nicer. I'm just going to copy everything, x plus 3 over 5 equals, instead of y, and just use our new symbols, f inverse of x. That's our answer. That's our inverse function, and we're done. And then technically, if we have time, we could check number 6. Eliza. Yeah, I want to check and see that really everything undoes, like the one function undoes the other function, and we want to check it in both orders. I'm not going to check here, but it's good practice to make sure that you get back to x. If you start with x, you should end up getting back to x. And then finally 7, Hazen. Reveal, revel, we got a revel. Let's see, I need to, all right, here we go. Okay, got it? All right, next page. Let's try number 4, Sam. Okay, so let's think about this guy. First, the domain. To refresh my memory here, is domain the x's or the y's? Domain is the x's, so let's find the domain. So I'm looking for the x's that make sense. Now, what part of that function is kind of scary in terms of having x's that are illegal? Is there's a square root, and we know we need to make sure that the thing inside the square root is not what? Not negative. So said another way, you need the x cubed plus 8 to be on the good side of the number 0. What's the good side? Greater than 0, right? That's how you make it not negative. Eric is saying equal to is all right. Is the square root of 0 okay? Yes, it is. So this is what we solve. Now, solving this is something we've never tried solving before. I mean, there's an inequality with an x cubed in it. We haven't done one of those. They are kind of tricky, but we're not going to do too much with this. Let's just say that, let's pretend that it's equal to 0. What value of x makes that equation true? Everyone agree -2 is the magic cutoff number? Is -2 good or bad when you plug it into the function? It's good, but just barely. We're allowed to take the square root of 0. That's what would happen if you plugged in -2 for your x. But now we got to pick numbers that are on the good side of -2. Pick a number that's way bigger than -2. Bigger than -2. 100. If you plug in x equals 100, are you going to be okay, or are you going to have problems inside of that square root? You're going to be just fine, right? 100 cubed, very big positive, add 8, I can take the square root. So it feels like numbers bigger than -2 are fine. Let's pick a number less than -2. -5, I heard that one first. If you plug -5 into the x, f of -5, square root -5 cubed plus 8. Anybody know -5 cubed? -125 is good. Plus 8. Is this going to be okay? No. So it feels like -2 is my cutoff. Numbers bigger, like 100, are fine. Numbers smaller, like -5, are bad. Can you guys take that and write the domain using interval notation? Where does this domain start? At -2, that's the smallest number that's okay. How big are the numbers we can plug in? Forever, infinity. What do you put at -2? Square bracket, including -2. -2 is fine. At infinity, always parentheses. Infinity is not a number. You can't plug infinity into this thing. It's not a number, but it's a symbol that means as big as you want. Okay, that's the domain. The domain of f is the same as the range of f inverse, but to find the range of this, it requires some work. Let's think about this. The square root function. Do you guys know what this thing looks like? Could you make a real quick, very rough sketch without your calculator of y equals the square root of x? So a few people know what it looks like. Y equals the square root of x. So there's y equals the square root of x. If you were to continue it, you'd get the same parabola that we were familiar with going up. Y equals x squared is the up parabola. This is the sideways parabola, but you only get the top part. Okay, so that's y equals the square root of x. Is domain x or y? Sorry, is the range x or y? The range is the y's. So looking at this function and just thinking about the y's that you get, it feels like we get y equals 0. That's our starting one. And then how high does it go? It goes up to infinity. So the range of the square root of x starts at 0, goes up forever. This x cubed plus 8, it's complicated, but it's the same. If you plug -2 into the function, f of -2, what do you get? You get 0. So that's our bottom. We're still going to get 0. It's not going to be there anymore, but we'll get to y equals 0. And then if you wanted to get bigger and bigger numbers, well, you could just plug in bigger and bigger x's. If you plug in x equals like 2, you'd have some square root. If you plug in x equals 5, you have a bigger square root. Plug in x equals 1,000,000, you're going to get a really big square root. So range is oftentimes really, really tricky. And so if you didn't get that whole explanation, no sweat. We're just going to say the range of this function is the same as the range of the square root of x function that we saw above. Okay, what was the last piece of this question? Finding the inverse. You guys find the inverse and we'll call it a day. Algebraically, what do I have to do first? Square both sides, right? You're trying to get your hands on y. It's buried inside of a radical. So square both sides. Still trying to get my hands on y. Subtract the 8. And what's the opposite of having y that's been cubed? Cube rooting. And then just the last piece, instead of calling it y, what are we saying? F inverse of x. Okay, we will pick up right here on Wednesday. Have a good day.